refrigerants these days are becoming very important. They were always important, but they are becoming very important because a lot of the regulations are driven around the refrigerant. So refrigerants are talked about almost in all HVAC and our forums. So before I start on and get on to the detail of you know this topic, let us just start with history of refrigerants, or even before we start with history of refrigerants, let me just ask or throw a light on what role refrigerant play. So refrigerant essentially is the media, or is the substance which provides the cooling to the refrigeration and air conditioning system. Now, how it happens is, there is a evaporator, mainly in vapor absorption, vapor compression system. So in the evaporator, we generate cooling, and how we generate cooling is we let this media which is lying in the evaporator to evaporate, means change phase from liquid to vapor. Now when this liquid to vapor vaporization happens, it extracts heat from this liquid. So this liquid refrigerant becomes cooler, and as it becomes cooler, we take that cooling for our desired cooling effect. So whether it is air conditioning or a refrigeration or any industrial or process cooling, so the lowering down the temperature actually happens in the evaporator. Now, when we call it as a cooling coil or cooling chamber or evaporator, here the important thing to know is, as the evaporation is happening, so the liquid level is going to come down, and we need to constantly extract vapors. So for constantly extracting vapors, we use a compressor because we need to pull all these vapors from the evaporator. Now, when we are doing so, the compressor discharges that to the condenser. When it discharges that to the condenser, because it's in the vapor phase and we want that now to convert it into liquid phase, so we take it to a level, a pressure where the phase change can happen at that pressure. So that is a condensing pressure depending upon the media, air or water or something. So it condenses back to liquid, and then we want that liquid returned back to the evaporator because the liquid level in the evaporator is coming down. Now, since we don't want evaporator to be flooded, or to have lot of refrigerant coming in, what we do is we provide a restriction, because only some amount of liquid should come back to the evaporator, and that is where we meter or control the total liquid which is entering into the evaporator through the expansion device. So if you see all those four components, the evaporator, condenser, compressor, expansion valve, the media which is connecting all of them is refrigerant. What we are getting cooling or heating is from refrigerant. So refrigerant plays a very significant role. Refrigerant is like the blood of the refrigeration and air conditioning system. And as something goes wrong to us as a human being, the very first thing we do is to get ourselves tested. And what probably a physician or a medical practitioner is going to do is going to check some temperature, which is your body temperature, and probably pressure. So pressure, when it checks for, it's the blood pressure which it checks, and we know heart is pumping the blood, so he takes kind of a the evaporator pressure and condenser pressure kind of thing. So similarly, if we know the properties of the refrigerant, uh, where the refrigerant is in what property, what state, probably we can find out if everything is going well in the system or not. or there is some modification required or not. But do all systems have one refrigerant? No. They may have different property, different significance. Similarly, how we all have different blood groups. So it can be A positive, B positive, and so on. So there are different refrigerants which have different properties, and we can't interchange those. We may interchange some of those, but not all of those. So refrigerant is playing a very significant role in our systems. So to start with, about the history of the refrigerants, the refrigerants started with the system when it started in 1830s, and it was ether which was used, then air was used, ammonia water was used, carbon dioxide, ammonia, sulfur dioxide, and then hydrocarbons were tried out in 1920s. But as you see this list, there were a lot of refrigerants which were used, which were essentially used what was available. So whatever was available in those days, a engineer or a researcher will use that to make a refrigeration or a air conditioning system, and that is where it used to become a refrigerant. But if you see all these refrigerants, there was some or other problem. So either they were toxic, or they were flammable, or they had the stability issue, or they were not giving the desired cooling effect. So what industry said that we want something which is non-flammable, should have a good stability, it should last till the system life, and should have low toxicity, because if it leaks out, there are people around, it should not be highly toxic, and it should have a boiling point of minus 40 to 0 degree centigrade. Now, this is something which is very interesting. This is something which is in those days, in 1920s, when industry was looking for a good refrigerant, those time they gave this, listed down this requirement of minus 40 to 0 degree centigrade. Even today, it is somewhat correct, but not in for all the cases. So why this, boiling point? Rest we know, non-flammable, non-toxic, or good stability. We know why they were looking for, but why they were looking for minus 40 to 0 degree centigrade of boiling point? This is something which is interesting. As we talked about the evaporator, what they were considering at that point in time, that if people are going to use this refrigerant for air conditioning. Now, say for example, for air conditioning, if you want 20-degree temperature in the room, then you need 10-degree air temperature. If you need 10-degree air temperature, that means your coil temperature on which we are going to get the cooling is going to be around 0 degrees centigrade. Now, 10-degree delta is that time they were taking in 1920s we are talking of. Now, if it is going to be 0 degree, we wanted that even at 0 degree, the refrigerant should be not under vacuum. So its boiling point should be 0 degree on less than 0 degree. Should not be more than, because if it is more than 0 degree centigrade, the evaporator will go under vacuum for air conditioning, and we don't want it that, because then the air will go in if there is any leakage. And in 1920s, designing a leak-free system was not easy. So they were considering that something which is running as refrigerant is going to always leak out. So that's why they said 0 degree. And why minus 40 is because if they go less than minus 40, then the pressures are going to be really high, specifically for the condenser. So it's going to be really tough for them to make the system viable, practical, and leak-free for such high pressures. So what they listed was from 0 degree to minus 40 degree centigrade boiling point is something which is very good, suitable boiling point for them. And this gave a very good start to the industry. We got in 1928, Thomas Migley, who was working with GM. That time he came out with a refrigerant called R12, which was known as Freon 12, because this General Motors subsidiary Kinetic Chemicals was then taken over by DuPont, which is now named as Chemours. So In 1928, he came out with 12, which was meeting all these requirements. 12 has a boiling point of minus 29 and non-toxic, non-flammable, and all that stuff. So everything went well from 12. There were other refrigerants which came out later on, like 22, 11, and other stuff, because when you are making and developing application, other things also came up. But the interesting thing came in 1970s when the concern of ozone depletion was studied by Roland and Molina, and they showed that yes, these CFCs, which are very stable, they used to be, because industry in 1920s was looking for stable substance. So these were so stable that they will not break down for hundreds of years. And if they don't break down for hundreds of years, these molecules will reach out to ozone layer on the stratosphere and then slowly try to break down over there. And the disaster was the breakdown components are going to give a chain reaction. So it's not going to just end up by breaking down. The components will further break down the ozone. So that's how the key concern came in, and we had to had a monitor protocol in 1989. This monitor protocol was to handle all ozone depleting substances, which were majorly CFCs, but also some other chemicals, HCFCs, and other halogenated compounds. But yes, majorly CFCs and HCFCs. And this is probably one of the international's most successful environmental treaty, where globally everyone came together and very beautifully kind of phased out for most of the substances. There are still some which are left, which in some geography, including India, there are some which are ozone depleting substances which are still in use, but they are still under phase out schedule, so they will be phased out soon. In 1990s, all of these were also recognized. CFC, SCFC, and HFCs were also considered and came out as greenhouse gases. So another set of regulations also started to come. Now, when we talk of refrigerants, there are a number of refrigerants. In these charts, mainly we will focus on fluorinated, because more than 90% of the entire industry works on fluorinated refrigerants. When we talk of fluorinated refrigerants, we are talking of essentially CFCs, which are chlorofluorocarbons. These are derived from hydrocarbons, and we have chlorine and fluorine attached to carbons. So it's a chlorofluorocarbon. Then we have hydrochlorofluorocarbon. So if we add hydrogen also to CFCs, the atmospheric light come down. We'll talk about this in later charts, but it is hydrogen, chlorine, fluorine, and carbons. And then HFCs, where there is no chlorine. There are also hydrocarbons directly used, but mainly these are the three categories which are used as refrigerant in our refrigeration air conditioning system. Now, if you need to understand the refrigerant chemistry, you can see from this triangle. Now, in this triangle, if you see, there are three components on top. Let me just take a pointer. Yeah. So if we see, this is hydrogen. Now we all know hydrogen is flammable. So any refrigerant which has higher number of hydrogen atoms is going to be towards flammability. Now fluorine, when we know fluorine is having very high stability, it increases the atmospheric life. Now when it is increasing the atmospheric life, it is going to have a penalty in terms of environmental regulation, which is global warming. So we don't want that also. But earlier these days, this was something which was very good. So we would use fluorine to increase the atmospheric life. But now we have another challenge of GWP. Chlorine, it increases the ozone depletion potential, ozone depletion. So we don't want higher chlorine, because, or in some cases, zero chlorine. And that's where we used to work in terms of CFC. When we talk of, we are somewhere here. When we talk of hydrochlorofluorocarbon, we are somewhere here or here. When we're talking of only hydrofluorocarbons, we are somewhere here. So you can see, and this is the area or the gas when you have very high hydrogen is flammable substances. This light blue, what you're seeing are the toxic substances, because this absence of fluorine leads to high toxicity of the molecule. And here are something which has very high atmospheric life, so we don't want these fully halogenated substances also, so we want a balance. So now if we look at, there are problems and the advantages of all three. So what we need to live with is figuring out what best we can come out for what application. That's why it's not one single refrigerant fitting all the applications. There are different refrigerants for different applications. If we talk of CFCs, uh, CFCs, which is chlorine, fluorine, and carbon, since there is a chlorine, there is ozone depletion, which is going to happen because of this, because the chlorine is going to break down the ozone layer. So it will make O3 to O2, and that's how it's going to have a problem. Manufacturing of CFC and the CFC based equipment have been banned across the globe now. So there is no CFC based equipment or CFC which can be produced for refrigerant application. For certain application, there can be some essential use which may be still allowed, but for most it is already phased out. HCFC, as we were talking, when we add hydrogen, we reduces the atmospheric life. When we reduces the atmospheric life, say for example, for CFCs, if the atmospheric life is, say for example, 700 year, if we add hydrogen, it comes down to say 10 years, 12 years, 15 years. Now, this 10, 12, 15 years is very good as compared to CFC, but it is still not very good because the global warming, it has still a very big role to play. So at CFCs, there is chlorine and fluorine both present. So its ability to damage ozone comes down drastically. Say, for example, if CFC 11 or 12 was 1, for at CFC 22, it's going to be 0.055. So yes, it comes down, and that's why there is a different phase out schedule. So 22 is still being used in India. It's under phase out schedule, so it's going to be 0 sometime. But as of now, some amount of 22 is being used. If we remove the entire chlorine, we are talking of HFCs, hydrofluorocarbon. Now, since there is hydrogen, the atmospheric life is very similar to what we have for HCFCs. And since there is no chlorine, so there is no ozone depletion issue with it, but there is still global warming issue. So if we have this global warming issue, we need to figure out how to handle this global warming issue. So we talked about the basic and the history. Now we come to the important aspect, which is also part of your probably curriculum, is the nomenclature and the safety classification. Now, when we talk of the nomenclature, normally a refrigerant is given with a number. So it may be starting with R. R normally stands for refrigerant. It can be CFC, HCFC, HFC, PFC, or hydrocarbon. Sometimes instead of R, you may find people writing CFC 11 or HCFC 22. So that is also used in industry. And then there would be a number. Now, how this number comes in is this formula. So the number is CHClF, which is carbon, hydrogen, chlorine, and fluorine. So these are the four key things which we need to know. Now, if you see here, this is the formula. R, which is the refrigerant, K minus 1. What is K? K is carbon, minus 1. So if the number of carbon are 2, we are going to put 1 over here. If the carbon is 1, we are not going to write anything because 1 minus 1, 0. So we are not going to write anything over here. Now, L plus 1 is going to be the second from the right, from the left, sorry. Second from the left is L plus 1. What is L? L is hydrogen. So if hydrogen is 2, we are going to write here 3, and N is the number of fluorine. That's straight. So if we are talking of a molecule which is having 2 hydrogen and 2 fluorine, 0 chlorine. So what we are going to write for 2 fluorine, we have 2 here, and for 2 fluorine, 2 here, and 2 hydrogen means 3 here. So we are talking of 32, and since the carbon is only 1, so 0. So R32, which is a commercial refrigerant, is having 2 fluorine, 2 hydrogen, and 1 carbon. Fine. So this is the way normally the nomenclature will work out to. So let me see if I can grab a pen. Yes, I can grab a pen. So now I take a pen and let me write. So we have, see, I'm sorry, excuse me for my writing. It's not that great. So I'm going to give you a small, a different idea of putting it across. So we have, say, 2 fluorine, 2 and 2 hydrogen. Fine. Now this is, we just figured out it's R32 as per this. We can also figure out whether it is R32 or what through a different formula or a thumb rule or a cheat code. Now, what this cheat code says is whatever is the refrigerant number, if you just add 90 to it, so I'm just adding 90. If I add 90, what I'm going to get is a direct allocation. So we have 122 means 2 is the number of fluorine, 2 is the number of hydrogen, and 1 is the number of carbon. If we put 1 carbon, 2 hydrogen, 2 fluorine, there is nothing left for chlorine. That's done. So that means this is difluoromethane. Now let me just do it one more. Say I take R, or let me go to the next chart. Yeah, this is so here we have CFC 12. Now for CFC 12, we do the other way. The book way is this way to do the long calculations, or we just used this way. 12 plus 90 is equal to 102. So we have fluorine 2, hydrogen 0, chlorine carbon 1. So if we keep 1 carbon, we put 2 fluorine, and there's no room for hydrogen. That means rest is chlorine. So what we get here is for R12 is difluoromethane. Fine. Same way we do it for 123. So if you want, you can do, but I don't see we have too much time for it. So we can probably do it later. So there is also sometimes a alphabet which is assigned. What is that alphabet? That alphabet is for isomer. Say for example, for 134A, if we take 134 or 134A, in both cases we are going to have 2 carbon, 2 hydrogen, and 4 fluorine. Now there are 2 ways of putting that across. One way is this way, where on 1 carbon there are 3 fluorine, and on another carbon there are 2 hydrogen and 1 fluorine. Whereas there is another way wherein each carbon will have 1 hydrogen and 2 fluorine. So this way or this way, both plays a significant difference in the properties of the refrigerant or the chemical. Now, since these are isomers of each other, so we need to differentiate them in the number. Now, to differentiate, we give A. Now, A, B, or a small alphabet. Now, how that happens is if we take this one, where there is no difference in the molecular weight attached to this carbon versus this carbon, everything remains, if we subtract, it's 0. Here, if we subtract, it's 36. So 0 and then 36. If there was any other option, which is say 40, 50 or something, it could have been 134B or something, but in 134 case, it's only 134 or 134A. So this is how we assign 134 or 134A. Just to give you an understanding of what we have done over here is fluorine, there are 3 molecules, hydrogen, there are 2, and here fluorine 1 on this carbon and this carbon. Now, if we take 3 fluorine and molecular weight of fluorine is 19, so 19 into 3 minus hydrogen 1 into 2, fluorine 19 into 1 is equal to 36. So that's what we are doing the calculation over here and here, and that's how we calculate whether we are going to give A, B, or C. Now, if we are talking of an ethane series, when there are in ethane series, or sorry, this is the same where we have A or B. So this 18 versus 54, so we got A, and this is the minimum which we can get, so there's nothing on it. Now, if we talk of propane series, in propane series, since we know there are 3 carbons, now in 3 carbons, the terminal carbons are going to behave like a ethane series, whereas the central carbon, which has only couple of options, because we have only 2 open spaces or 2 valencies open for this. So it can be either 2 chlorine, 2 fluorine, 2 hydrogen, or a chlorine fluorine, hydrogen chlorine, or hydrogen fluorine. So if we give a number to all of these, which is A, B, C, D, E, F, so if we give a specific alphabet assigned to this middle carbon, then we can assign or come out with the refrigerant number easily. So for 245 FA refrigerant, if we add 90, we do the same way. We calculate the total number of fluorine, total number of hydrogen, and total number of carbon and chlorine for this molecule. Now, what would be there in the center is which is given by this first alphabet, which is F here in this case of 245 FA. If it is F, means 2 hydrogen. Now in this case, the center carbon, which is this one, will have 2 hydrogen. Now if this will have 2 hydrogen, means rest everything is going to be assigned to these, and this now will be calculated based on what we see in the nomenclature for ethane series. Fine. So it's very simple. Isomers A, B, C, D again will work out based on the molecular weight difference between this carbon and this carbon. So that's how it's going to work out. So when we talk of methane series, ethane series, propane series, then for beyond these, there are isotopes. So say 400 series, isotopes and zeotropes are blends. Now these blends are something which may or may not behave like one. So if they try to behave like one, we call them 500 series azeotrope. If they fractionate in the vapor phase and have a differentiation, then we call them zeotropes, which is 400 series. Now, how the number is assigned to a refrigerant, how 407C is called 407C and all, is something which is important. For zeotropic blends, when there can be a fractionation happening, if anyone comes up with a blend, say for example, a blend of 32 and 125, if one company comes out that, hey, we want to make a refrigerant with these 2 components, we go and register it with ASHRAE. ASHRAE gives it a number, say for 10A. If another company comes in and say that, hey, we want to use the same components, but in a different ratio, then that ratio is also going to be written down and another alphabet will be given for the same number. So 410B will be given. And note, these AB in the blends are the capital one, whereas in the isomer, it was the small one. So A, B, C, D, E will be given to the different composition for the same components. If the components also change, if we add 134 into it, they are going to give another number, say 407. Now again in 407, if there are 3 components and the composition keeps changing, then A, B, C, D, E, F will be continued to give. And 407F is also very popular refrigerant gas. So there can be very good number of combinations of percentages which can be common. Azeotrope, as we know, they don't fractionate. So here the nomenclature remains same. So anyone comes up with a new mixture, they go and register with the ASHRAE, a number is given, and then based on the composition, A, B, C, D, F is given, in the sequence of how they are registered with ASHRAE. Then there are miscellaneous organic compounds, so butane, pentane, ethyl ether, so 600, 601, 610. Some inorganic compounds, so which starts with 700 range. So now when we talk of 700 range, then the molecular weight attached to it is given. So 717 is ammonia, because ammonia NH3, you have N for 14 and then H1 into 3, so it's a 17. If the carbon dioxide and nitrous oxide both is 44, then nitrous oxide is given A, so for 744A, this is only for theory. Normally in practical circumstances, ammonia is used, carbon dioxide is used, but nitrous oxide, I am not aware of if there is any usage. Propane series, if we have a propene, means there is a double bond, unsaturated one. So in that case, if you see, now when you see here, which is 1, 2, 3, 4 YF, 1234 YF, this is actually a replacement of 134A, and this double bond helps in reducing the atmospheric life of the molecule. If you remember, when we were talking about the CFCs, we were talking of atmospheric life of say 700 years. We came down with adding hydrogen to say 10 years or 13 years. If we add a double bond, it becomes unsaturated, and then the life will become like 1 day, 2 day, 5 day, 10 days. So if the life of the molecule comes down, it's good for environment because it's going to break down easily. So it's not going to last long. So it's not going to contribute to the global warming for very long. So the global warming potential is going to be very, very small. But imagine if this molecule breaks down in the environment, we need to also consider that it should not break down in the system. So this should remain stable in the system, but when it comes in the atmosphere, then it should be able to break down. So fishing out these chemicals, distillation of these refrigerants which have unsaturates is something important, because we don't want any impurity which is going to adversely impact the life of the refrigeration air conditioning system, because the life of the refrigeration air conditioning system can be anywhere from 5 years to 50 years. So we want a very stable in system kind of a refrigerant, unstable outside the system. Now if we talk of this one here, now as we were talking of propane, on the center carbon there were two options, one up and one down. Here in the center it's going to be only one, because there is a one double bond between two carbons. Now if this is the case, then the center carbon will either have fluorine, chlorine, or hydrogen. So we give X, Y, or Z. Whereas this carbon which is attached to this through double bond will now have only two open, which is similar to what was the middle carbon of the earlier one. So we use the same A, B, C, D, E, F for the terminal double bond carbon, and we use X, Y, Z for the center carbon. So say for example for 1234 YF, if we same add 90, we are going to get the number of fluorine, hydrogen, and carbon, and we need to come out with the chlorine. In this case of 1234 YF, there is no chlorine. So since it is Y, so means center will have fluorine, and then is F means the the carbon next to this, which is this one, will have two hydrogen. So if we have this, then whatever is left will be left on this carbon, which is CF3 CF CH2. Fine. So this is about the nomenclature of all the refrigerants, or the list of the refrigerants is also available in ASHRAE standard 34. You can see there are a number of things available on this. Now when we talk of the toxicity, or the safety classification, there are two things. One is the toxicity, second is the flammability. So if a substance or the refrigerant is practically toxic, we call it as B, class B, which means it's practically toxic in the system. So it is on TLVTWA, which is threshold limit value on time weighted average. Means if a person on a long term is exposed to this molecule or substance, then over a period of time, it's going to have a adverse impact on that person. So it's a long-term exposure classification kind, where we classify as of now as A or B. A is something where we are not going to see any major impact. So there we call it as practically non-toxic, and B as toxic. Flammability, when we talk of flammability, we have given is, so in toxicity it's A or B, in flammability it's 1, 2, 3, and 2 is further subdivided into 2 and 2L. Now flammability classification, if there's no flame propagation, means it's kind of a practically non-flammable, we call it 1, and if it is highly flammable, we call it 3. If there is a flammability but we feel we can manage with something or other by looking at their flame properties, then we call them 2 or 2L. So if there's no flame propagation, 1. If there is a flame propagation and there is a LFL, which is lower flammability limit of 3.5%, and a heat of combustion less than 19,000 kilojoule per kg, then we call it 2L. If it is more than 19,000 and LFL is less than 3.5%, we call it as 3. And for all 2, if there is a burning velocity of less than 10 centimeter per second, then again we call them 2L refrigerant. So we have safety classification, we have A, B, and then we have 1, 2, 2L, and 3. Now we can put all the current refrigerants into this classification matrix. So what you see on the top is A3, A, B3, which are highly flammable and non-toxic versus toxic, and A1 is the refrigerant where most of the refrigerants used to work was A1, where it is going to be non-toxic, non-flammable, and we can easily use. So 134A, 410A, all of these refrigerants are A1. R32, which is A2L refrigerant, is something which is common these days. We also see propane in a lot of application, including the room air conditioners. And for a limited quantity of the refrigerant, we can safely manage propane. And when we talk of safety classification, we need to manage that safety aspect of that refrigerant. It's not that we can't use. We can use any of the refrigerant. The only thing is we need to be sure of how to handle, how to manage that specific refrigerant in that system. So if we see on this graph, we can see anything where there is a coming towards the red is something which is higher risk versus yellow. From a flammability perspective, there are two things which are important. One is the chance of the flame, and second is the effect of the flame. So how easy or difficult is for a substance or a refrigerant to get ignited is something where we talk in this chart, and the next chart would be what happens if there is a fire of this substance. So now here, if we see, there are two aspects. One is the minimum ignition energy, and second is the lower flammability limit. What is the minimum amount of the refrigerant required to be present in the air, which can make it ignitable? And what is the minimum ignition source or minimum ignition energy required to ignite that substance? So one, there need to be a fuel. Second, there need to be a source of fire. So a 5 ampere switch or a static energy, all these have different minimum ignition energy. So if we see, the higher is means we need a bigger energy source. So a small spark can ignite all these, but not 1234 wire. And a very small amount or concentration in air can ignite these, but not this. And if you don't see R32 here, which is commercially available, because the lower flammability limit is 14. So it's very far. The effect of flame is very similar when we talk of if there is a higher impact of that burning refrigerant means it is generating too much of heat and it flows very fast. Burning velocity is higher and it produces a lot of heat. It's dangerous. Whereas a substance which have lower heat of combustion and does not flow and it may die out of its own is lower flammability limit, which can be classified as to A2L, which is less than 19,000 kilojoule per calorie and less than the burning velocity of 10 centimeter per second. So this is A2L. You can also see 134A, which is A1 here because there is a heat of combustion. There's no burning velocity. So it's A1 refrigerant. But this is something which is important for us to know the property, flammable property of the refrigerant, so that we can know how much refrigerant we can charge, whether we need to use the power circuit or control circuit as explosion proof, what type of spark if generated in the system can be okay or not okay. So all that stuff comes from these flammable properties. This is the same properties in a tabular form. I'll share these with you. The another aspect comes in the refrigerant blend. As we know, the environmental regulations are forcing these refrigerants out. There can be different refrigerants coming out as a blend. Now, in a blend, we match the properties of a refrigerant by mixing two or more refrigerants. So this is the way we do. You need to always take liquid from the cylinder so that you're getting the complete fraction. Otherwise, in the vapor phase, there can be a fractionation, specifically in the zeotropic blends. In a normal cycle, if we see the boiling is going to be straight, means it's going to be at a constant temperature. Whereas in case of zeotropic blends, the boiling on is going to start at one point and it's going to end at other point. The temperature difference between these is called as temperature glide, and this gives us a very interesting view in terms of when we are designing or managing the heat exchangers, so evaporator and condenser. So we need to look at the dew point and the bubble point and take it into consideration. Refrigerant properties, these are something which are important properties. First of all, environmental property, we talked about the ozone depletion, we talked about Monroe Protocol. Global warming also, we talked about the global warming. So the potential associated with any gas for global warming is called as global warming potential. There are a number of things attached to it: Kyoto Protocol, total global warming impact, life cycle climate performance. These are all the environmental properties which are assigned with each and every refrigerant. Now, from a thermodynamic perspective or from a refrigeration system perspective, there are some more properties which are required. One is the refrigeration capacity. Now, this is something which is very important. When is a refrigerant is entering into the compressor, how based on that specific volume of that refrigerant at the entry of the compressor, we come out with this capacity to compress from the compressor what is going to be the cooling generation out of it. So different molecules will have different refrigeration capacity. So the size of the compressor can be larger or smaller based on that specific volume. So that defines the refrigeration capacity of a refrigerant. Operating pressures, we want system to be operating both in the evaporator and condenser at the positive pressure, and it should not be very high positive pressure, because if it is too high positive pressure, we have a challenge. If it is in a negative pressure also, we can manage, but then we need to design our system, and which makes it slightly complex to design to operate in a negative pressure. So under vacuum evaporator kind of system. Compressor also requires lubrication, and since the refrigerant is flowing, we want good oil miscibility so that it lubricates the compressor, and it should not leave the oil while it is in the expansion valve or in the evaporator, because at the lower temperature the miscibility capacity or the oil carrying capacity of the refrigerant may come down. So we want a very good miscibility. So oils are specifically configured for some of the applications to meet this desired property. Chemical stability, it should be chemically stable in the system, should not disintegrate. Thermal conductivity, we need a good thermal conductivity in the liquid phase. Discharge temperature is another important point for us to know, because as the compressor discharges the refrigerant as a hot vapor, if the discharge temperature goes very high, then the disintegration of the elastomers or the oil or the other parts is going to start. So we want normally a discharge temperature to be less than 100 degrees centigrade, which is easy for us to manage. Normally we prefer from 70 to 100 degree is something which what we prefer. We also look for a good dielectric properties, because nowadays a lot of compressors are hermetically sealed and the motor cooling is done directly from the refrigerant. So if we are using direct refrigerant for motor cooling, we need a high dielectric properties so that we can continue to run the system for long. So these were about the properties. There are a number of new refrigerants which are coming up. If we see here on this, these are 1,3,4-A alternatives. So 1,3,4-A is tetrafluoroethane, which is used in automotive air conditioning as well as in refrigerator as well as in chillers. If we see here, based on the classification, the green is something which is A1, non-toxic, non-flammable, A2L is yellow, and A3 is red. And for 1,3,4-A, which has a global warming potential of 1430, the substance which can give a very good comfort in terms of GWP is going to be mildly flammable. So there is not very good options available in very low GWP in this case. R22 commonly used in room air conditioner, now getting moved to R32 and other refrigerants. So same story here. If we need to go down in terms of GWP, not very good options available in green, not very good options available in yellow. Yes, in A3. So propane is very good refrigerant which is used. R32 is also used, which is 675 somewhere here in A2L category. But yes, not very good options available. 404A is a refrigerant, so green. 404A will have around 4,000 of GWP. Carbon dioxide replaces 404A, which gives a very good replacement. But in certain conditions, like in India, it's not adaptable for all the applications. For only limited applications, it can be adapted. So for rest, we need to look for these kind of alternatives, or this kind of alternative where for a very large charge size system, we look for like N40 type of refrigerant, which can bring it down to like 1,300 or 1,500 GWP as compared to 4,000 of 404A. And for medium, we can get, say, 200, 300 GWP. Fine. So then 410A, here we have absolutely nothing. 410A, carbon dioxide is only for certain refrigeration application. For air conditioning application, it's A2L. So A2L means for room air conditioning, probably we are going to work in future with only highly flammable or mildly flammable. So having a non-flammable option for us for room air conditioner is going to be a really big challenge. So this is all I have, and we have just 3 minutes left. I'm sorry, I was slightly, this was too much charge, but this is best I can do in this short time. So if you have any question, any of you can just throw that to me.